Thank you. Good morning, everyone. My name is Yizhou. I'm from University of California, Los Angeles. So today I will present a long paper, Primal Extended Position-Based Dynamics for Hyperelasticity. So let me begin with the background a little bit. So within the scope of this paper, we're primarily focused on simulating deformable solids using hyperelastic models. So the existing candidates for our choice are Newton's method and XPBD. So XPBD, short for Extended Position-Based Dynamics, is a very powerful simulation method. It removes some of the limitations of PBDs, and it can handle real-time simulations in the manners that if the computational budget is limited, it still stays robust and stable and gives a very plausible visual look. So here I present a basic example where I have a simple block mesh with the left end clamped and just dropped under gravity. So the far left one is a simulation I run with Newton's method to convergence for like the ground truth. But the other four are run with the same computational budget of 200 milliseconds per frame. It is small, but actually not quite small enough for real-time simulation. But in this case, Newton's method does not stay stable and essentially explodes. But XPBD and our algorithms would remain stable. And that's the sort of the goal I want to achieve. So let me give a broader picture of what we want to achieve here. So our essential goal is trying to come up with a unified solver that can both do real-time simulation and high-quality offline simulations for deformable solids, especially for muscles. And well, we do a background check, and we have Newton's method and XPBD that already exist. And Newton's method can converge, and when the computational budget is sufficient, would give very high quality visuals. And XPBD can, on the other hand, can do very good real-time simulations, even when it is unconverged. However, both of them cannot handle the other case. So we want to combine their advantages and address the limitations from XPBDs. So you see the other two methods are what we call PXPBD, which is short for Primary Extended Position-Based Dynamics. Sorry for the long name. As you can see, the check marks, they have both the advantage of the method, and also XPBD has another limitation, is that it does not easily apply to arbitrary hyperelastic models, which are exactly the kind of models that we want to use. We come up with another variation that's called FP-PXPBD here that addresses that limitation as well. So let me go a little bit more into depth for the XPBD algorithm. So it is a really fast algorithm, and it does that by doing some approximations. So the bottom equation here is essentially the nonlinear system that XPBD tries to solve, but it's pretty hard to solve. So XPBD makes the approximation by removing the two red terms on this equation here. So the left term is not so important. It basically means an approximation to the true Hessian by using the mass matrix, and that's a pretty standard procedure. But the right red term, which is the G term here, which we call primary residual, it's pretty key for the actual convergence of the algorithm. And XPBD makes the approximation that this term is zero, which is wrong after the first iteration. And that leads to its unconvergent behavior. So here I show a plot of which try to support what I was talking about. So there's three curves on this plot. So there's primary residual, secondary residual, and the true Newton residual of the system. So as you can see, the red curve keeps going down over the number of iterations because the red curve corresponds to the H term in this system. And it keeps going down because it is considered in XPBD's algorithm, but the blue line stays flat because it's the missing G term in the system. And eventually it makes the yellow curve stagnate because, well, you need to reduce both the red curve and the yellow curve so that the true residual would actually go down. We try to fix this issue by simply first adding this primary residual term back into the full system. And that does not work. So what I mean by that is that you can just put G in here and it's non-zero and you can directly compute it. It's kind of complicated mathematical wise, but it would remain in unstable behavior in XPBD, which I show by this block example on the right. So the right one is just plain XPBD and the left one is just XPBD with that added G term, and it becomes unstable after a couple of frames. Another limitation of XPBD that we want to address is that it takes some work to adapt it to any hyperelastic energy. So the bottom left is the usual XPBD formulation of its constraints. So the energy has to be quadratic in terms of the constraint for we to use XPBD. But the general hyperelastic energy is not in that form. It usually comes from some kind of FEM discretizations, and it's in the form of energy density times the measures. And it takes some thinking to go from the right to the left. So here I give some examples of the types of hyperelastic models that we want to use. So after a couple of experiments, so we were focused on doing like muscle simulations. So after a couple of experiments, we realized like fixed co-rotating model and co-rotating model fiber were what we want to use. So on the far left, we were simulating a full human body, upper human body musculature in a passive way using the co-rotating model. And on the right here, it's just a simple block, but we use it to emulate the model that we adopt for simulating muscle contraction. So you can notice there's an activation parameter on the bottom right corner here. So first of all, the block just drops unactivated under gravity. But then after it's activated, it contracts and basically bounces back. And that's kind of that's the kind of visual effects that we were looking at. And now I explain a little bit more why it is hard to adapt the hyperelastic models in the XPBD formalism. So as I was saying, they are just different formulations. And the one very direct approach that we could do is to directly take the square root of the energy density and then just claim that to be the constraint in the XPBD formalism. But that would drastically decrease the stability of XPBD. So for example, I have a simple block simulation here. So I stretch and compress both ends of it. And the first one was simulated using this square root constraint formalism that I was talking about. So it just explodes after a while. And the middle one is using our FP-PXPBD algorithm. The full name I will talk about later. So it doesn't require such a reformulation, and well, it works fine. And the third one, it's actually plain XPBD with this model, but it takes actually quite some work to adapt it to those constraints, and it's actually a part of our paper if you're interested. So to sum up, we make the contributions to by doing a reformulation of the XPBDs that improves this convergence for hyperelastic models and also extends it to arbitrary constituted models. So before I go more depth into the algorithm, let me go back to the problems I was talking a bit before. So basically, our goal is to add G back into the system because it's the culprit that XPBD does not converge, but we can't just put it back in. So we came up with some way else, which is the second equation here. So we try to solve it by basically just doing fixed point iterations after the Lagrange multiplier is held fixed. So basically what I mean by that is that after lambda, which is the dual variable here, held fixed, we can just do fixed point iteration on the variable xkn plus 1 here to gradually reduce g. But unfortunately, doing a lot of iteration, a fixed point iteration on x is very costly. So because basically you have to update all the constraint gradients every time for each iteration of it. And that's almost the same cost as XPBD iterations. And we were trying to make it as real time as possible. So in the end, we take the approach of just doing one fixed point iteration. But it would actually reduce residual by quite a lot. And but then we realized it's kind of unstable in some scenarios. So we took the approach of blending the update from the fixed point iteration with the original XPBD update. So that's basically the second equation in here. As you can see, there's a parameter called nu, which we call linear blending parameter. A slight limitation of this method is that this nu parameter is a hyperparameter and needs to be user-defined. So it might differ for different simulations. So that's a little drawback here. But I mean, it does converge if you set it right. So another approach we took was that we made the observation that the Lagrange multipliers in the XPBD algorithm resembles the stress terms that comes from FEM discretization. So we just change it to the first Piola-Kirchhoff stress as the secondary variable. And by doing that, we can try to make sure G is 0 without doing the fixed point iterations I was talking about. So to be more specific about what we do here, we reformulate those G and H equations as before. So first we change the letter from lambda to p, and not just simply changing the letters, it means changing the meaning of those variables. So now for the dual equation, we have the classical equation coming from mechanics literature, where the stress is like dψdf. And this equation can be automatically satisfied by just computing p equals to dψdf. So we don't have to worry about the second equation. And now we can just plug the second equation back into the first equation for the system that we actually want to solve. It is actually pretty complicated mathematically. So if you are interested, I encourage you to read our paper in more details. So essentially, XPBD does a Gauss-Seidel update for each constraint. And we do similar updates for each constraint, but the computation is just totally different. And we try to solve the first equation here for every constraint. The thing I want to address is that when we are solving that equation, it involves solving a linear system of size usually 12 by 12 in 3-dimensional, because for each tetrahedron there's like 4 points and 3 dots for each point. So that's like 12 in total. And that still leads to like a large cost because inverting a 12 by 12 matrix is not easy. So we came up with this thing we call affine element basis, which is basically decoupling the true 12 DOFs into 9 DOFs of deformation degrees of freedom and 3 DOFs of translational degrees of freedom, which is the delta Fe and the Be at the bottom. And after doing that with some more mathematical tricks, the computational actually becomes really easy. You can read the paper for more details. But essentially, in the end, both the blended PXPBD and FBPXPBD has the per iteration cost very similar to that of XPBD, like usually less than 5% more of XPBD. But they do achieve a better convergence rate. So let me show a plot here. So this is the residual norm versus the number of iterations. So as you can see, XPBD would stagnate, and our variations, both of them would converge to desired tolerance. And more convergence rate on the residual part might lead to better visuals. So in this case, I show another stretching block simulation in here, for example. So this one is actually using the exact same model and XPBD algorithm from 2021 paper of McLean et al., which is called Neo-Hookean XPBD. And the first one is just simulated using the XPBD in that paper. And the second one is simulated using our FPP XPBD. And the third one is like Newton's method, round to convergence for the ground truth. So you can see that our algorithm is more converged because it's, it's basically the same as Newton's method. But XPBD is less volume preserving when it is compressed. Okay, so the second part I want to introduce is this thing we call grid-based variation. It usually works with XPBD and blended PXPBD. So the math background of this one is pretty lengthy. So this method is also known as like material point method, so short for MPM. I don't know if some of you might have heard of it. You can check the background in some MPM papers. So for example, the 2015 one called the particle in cell method. The spirit of this algorithm is basically just like for every time step, you create a Eulerian grid and try to approximate all your actual particles by the grid nodes. And you solve for the grid nodes for your actual DOFs. And we realized that we could replace the underlying solver, which is Newton's method that people has been using all the time, to either XPBD or PXPBD, and has better effects. So the left one is some screenshots that we took for a simple twisting animation of some blocks. So this is a demonstration of what grid-based BPXPBD can do. So we drop like a bunch of objects into a glass box and let them collide with each other. There's about 30 of them with a total particle count of 800K. So that's simulated with nu equals to 0.5. And basically, we want to use that to demonstrate the capability of our algorithm to deal with collision-intensive scenarios with very high-resolution meshes. And here, I want to present more data as well. So here, for the left, I plot out the residual norm versus the number of iterations for a given frame of the previous simulation. So as you can see, XPBD stagnates as usual, but our blended algorithm achieves similar level of residual reduction as Newton's method. But we noticed that the blended or XPBD has a much lower per iteration cost as Newton. So if we actually plot out the residual norm versus runtime, blended will eventually beat Newton, like in the later on. So that's pretty impressive. Okay, so here I present some more examples, some more nice animations from the grid-based variations. So this one is twisting the 4 bars and then untwisted. This one is just dropping more objects in the box. But the resolution of those meshes are much higher. So each dragon is about 200K vertices. Okay, now I want to introduce Chaos Flash a little bit. So it is sort of an experimental product of the core solver of which is our XPBD-based solver. So it's an experimental plugin in the Unreal Engine that is focused on doing deformable body simulations. And because of the advantages of our solver, it can be used to do both real-time simulation and also high-end offline simulations that can be used to train a machine learning pipeline. So let me play the video a bit. Oh, let me just. Okay, so One sec. Okay. So this one is basically showing a truck driving through the jungle. It was showcased on GDC earlier this year. So basically, its 4 tires are simulated and rendered in real time using our solver. And you can see as the truck drives around, the tire would collide with the ground, it bulges a little bit on the side and like get compressed in the collision normal direction. Okay. Oh, okay. And that was the real-time aspect of our solver. And now I want to demonstrate its capability to do high-end muscle simulations. So the result of this video here is first run offline and then cached and then played back. Let me explain a little bit of what's happening here. So the left one is like an actual human skeleton. So the underneath actual human skeleton is animated by artists. And then we attach muscle pieces to this human skeleton. And then those muscle pieces get to be simulated as the skeleton moves around and drives them around. And the right one is a volumetric human body mesh that gets simulated at the same time. So we simulate left and right at the same time. And then we bind them together so that the left one drives the right one. This is to emulate in real life that say if I move my arm around, my muscle first, well, I fire my muscle first, and then the fat layer over the muscles gets driven by the underlying muscles. And basically the right one is the fat layer. So, okay. So that's most of the content of the talk. So we made more development since this paper. And so basically we discovered that within the framework of XPBD or our variations, there are still limitations. So for example, the constraint can fight with each other, which is essentially really bad for quasi-static type of simulations. And we addressed that issue by doing a node-based framework instead of a constraint-based one. And by doing that, we actually had even much better quality of muscle simulations, which can be shown at the screenshot here. So that paper is on arXiv also. So if you're interested, you can check it out. So let me do a little summary of what we have been doing. So first of all, our method, PXPBDs, they address XPBDs convergence issues and allows for generalization of arbitrary hyperelastic models. And also the grid-based variations achieve same levels of visuals as the prevailing Newton's method. But our variations also have limitations. So for example, blended has a parameter that needs to be tuned. And the FP-PX-PBD does not generalize to the grid-based variation. And also it needs heavy optimization in order to be run that fast. And that might not generalize to some specific hyperelastic models. That's all. Thank you for listening. So I think now it's question time. So if you're interested in discussion, you can also email me at my email address here.